Okay, great. So, good evening, everyone, and welcome to today's session. Today, we will be discussing about the machine learning aspect. So, how we can use the machine learning in R. Um, so that we will be discussing today mostly. Okay. So before that, any questions on any previous topics or something? You can simply here. So we'll discuss that and we'll move on. Okay, so if there is no other questions, we will move to the machine learning part. So once again, welcome to the R4 data analysis course from foundation to advanced applications. This is a course offered by Department of Statistics, University of Calicut. So today we will be discussing about the machine learning using R. So basically, as of all of you know, like what is machine learning? So machine learning is a part of artificial intelligence, or it's a part of the umbrella of artificial intelligence, where computers learn pattern from data and make predictions or decisions without being explicitly programmed for each of the cases. Okay, so a simple idea can be like yeah, instead of writing a rule like for you people, you are getting the scores and all in every exam. So if you consider the exam point of view, then if you are getting a passing score greater than 50, okay, after calculating internal and external, so if your score is greater than 50, then you will pass. Okay, so instead of creating writing these kind of rules, like if score is greater than 50, then pass, we will let the machine learn from the rule from the data. Machine learn the data rule from the data. For example, we will be giving the past students data. Okay, your seniors data, like their exam results, study hours, attendance, etc. etc. So we'll be giving those data, and from that data, the machine learns that the student with high study hours and attendance usually pass. Okay, and also based on the exam result, these factors will also support those things, and based on that, we can actually create a model, and based on that data, machine learns these things, and then it predict the result for new students. Okay, so that is what basically we call it as machine learning. Instead of giving a rule again and again, so if we simply give the rules again and again, it will be a kind of a what we call as rule based learning. Okay, rule based learning, or it is automation. If there are simply rules is there, there is no learning is there, only rules are there, then it will be called automation. So a lot of things are automated now. You know, a lot of things like uh, once you know some packaging things and all, packaging industry, so it will be like mostly it will have this packaging process, and that will be automated. Like if you wanted to pack something with 100 milliliter of some product, and we need to pack it, so some process will be there, and the final product will come, and there will be one um, carry bag, like or a package will be there, and then the product will be filled into that package, and it weight, like if the weight is actually this thing 100 milliliter, then it will complete the packaging on that one, and it will go to the next bag. Okay, so that is automation. But if because that is a more kind of a rule based, if something actually happened like this and then it is completed. Okay, so that is rule based one. And when it comes to machine learning something and understanding the rule from the data without saying okay, this is the rule we need to follow, uh, s- that rule can be changed based on the circumstances as well. Okay, so if you are doing the automation, in automation what happen is, if you are having multiple bags, okay, for example we need to fill the product in different bags. So if the automation is set to be 100 milli packaging automation, then uh, regardless of like what is the capacity of the baggage, even if it is a 500 ml baggage or 250 ml baggage or 1 liter baggage, the machine will simply fill 100 milli because it actually working on some rule base, and it is actually restricting that filling a baggage to 100 milli. Okay, so that is called automation. But when the machine recognize which bag is actually coming and what is the size of the bag, and filling that bag with the amount that required to fill that baggage, then it will call machine learning. So there actually machine learns how to fill the product based on the bag capacity, and it is filling. So that is what we call as machine learning. Okay, so there based on the previous data, machine is actually learning something and then it is actually taking action. Now when it comes to the type of machine learning, there will be mostly we call it three type of machine learnings are there. So first one is supervised learning, second one is unsupervised learning, and third one is reinforcement learning. In supervised learning, the data will have labels. Okay, so these label data will be used for prediction. For example, we need to classify something pass or fail, spam or not spam. So there will be some labels. So based on the label that will classify. Or if we go to regression modeling and all, predictive models like regression and all, so there will be some factors that will have, for example, salary prediction, is prediction. So there will be some factors influencing this one particular variable, and that influence have some kind of a relationship, maybe a regression equation or something. So that is what we call as a regression model. So based on that formula or based on that model, we will predict something. Now, when it comes to unsupervised learning, the data has no labels, and that there it is actually find the patterns, and based on the pattern, it will classify. Okay, for example, clustering model. Okay, for customer segmentation and all. So there we don't have any labeled data, or we don't have a proper data for that, and based on the pattern in the customer uh, customer segmentation, it will simply classify the customers into different group. Okay, now also the association rules, and also sometimes we use the a priori algorithm and all. So it's more kind of like you are getting some product suggestion in Netflix, or Amazon or Flipkart or Mintra. So those things will be based on the customer segmentations, like some kind of a association rule, and we call it as a priori algorithm. So based on the a priori algorithm, it actually find the matches and all, and then based on that it will create some association, and based on that you will get some suggestions and all. Okay, some combo offers and all, so you will get it like that. Now the third one is reinforcement learning. There we will be learning by trial and error. This is actually the thing we are actually using in the robotics, or self-driving cars, AI agents, or games and all. So we are using the chat GPT, or so these kind of LLM models and all. So there also we are using the reinforcement learning. It will be based on the trial and error. So for example, if you are using any GPT models, then we are putting some chat to find something, and it is not finding the exact thing, then we can again ask, tell them, okay, this is not I want this one, okay, or this is not the way I need it in this way. Okay, so it will actually give you a better answer. So like that, if we tried it for multiple times, we will be getting the proper requirement that will be satisfied. So there we are actually using the trial and error method, and based on some learning we already have, the machine is actually trying to improve the learning based on our commands and all. Okay, for example, if a robot is actually trying to do some jobs and all, it won't actually fulfill in the first first time. So it will need multiple iterations and all, and then it will do the things perfectly. Okay. um, okay, so these are the methods we have in machine learning, and okay, these are the type of machine learning, and we try these things and use while performing a machine learning operations. Now, why we need or why we use R for machine learning? R is actually having a strong statistical foundation and excellent visualization. Now we have a oh, okay. Presentation slide is stuck. Okay, yeah, just a sec. Let me. Mm, yeah, thanks, Alvin, for pointing out. Okay, let me reshare once. Okay, I think the slide is having some issue. Um, okay, so thanks for the heads up. Okay, yeah. So I think the slide is having some issue, so we'll yeah, go through this one. So okay, so we okay, why we are using R? R is just because we have a good machine learning packages like Carrot and all now for our environment, and Carrot is actually classification and regression training. Okay, so that is actually Carrot, classification and regression training algorithm. So that is Carrot stands for, and so these kind of packages are also there, and we easy experimentation we can do using R. Nowadays R is actually adding lot of packages and all for machine learning. If you look a couple of years back, then R doesn't have that much libraries and all. Now R is also adding the keras and those kind of libraries. R is actually contributing, and we have a better options there. So this is the package we use mostly for our machine learning. Okay, so here Carrot is actually helping us to provide the data splitting, pre-processing, model training, model tuning, and model evaluation methods. And it is very powerful, like same syntax for many machine learning algorithm we can use, and it also has some built-in cross-validation functionalities, and it has easy performance comparison and all. Mm, so uh, we actually need these kind of these packages, so that will help us to perform the machine learning operations. So here I'm installing these packages, E1071 Carrot, Do Snow, and iPred, and XGBoost. Okay, so these are the packages I'm using. So this packages is 10 this is a dependency for caret and that will be installed. ipred and xgboost are dependencies for backed decision trees. Then and that will also help us to perform the decision tree method in caret caret package. Okay, so that is these packages actually do. Now we first load the library caret and the snow do snow package. Okay, so we do have this one also. Do Okay, so do snow is used to enable the parallel processing and for model training. Also, we can use the parallel. So parallel package is also there. So that will also do the parallel processing. Okay. So and iPred and XGBoost are dependencies for this one. Now, okay. Um, Okay, so first we will do a different one like so first here we are using a data. Okay, first we load the packages, these two packages, and now we will load the data. I have a data, so this is the data that is actually the Titanic data. So here we have the passenger ID survived or not during the Titanic crash, and passenger class 1, 2, 3 will be there, and name of the passengers, gender, then age, uh, so Siban, and these are the um, okay, these are the variables are there. Okay, so these variables are there. Now Now what we will do is first we will do the data wrangling process. So first replace the missing embarked value with mod of the value. So here you can see embarked value is actually having C, class C, Q and S. So S is actually having most of the uh, values are a part of S class. So we will be changing the embark class. Whatever is missing, we will be changing with S. Now we will also check the call sum of missing value. So age is having a lot of missing values, and other things we don't have any missing values as of now. So initially it had here our data is, and now if I check, so here um, embarked is also fine. Okay, so the if any missing values are there, we will be replacing that with s. And now we will take the summary of the age is having a lot of missing values. Then as we see here, age is having 177 missing values, and this data is having okay, let me clear the environment first, and then let's try it again. Okay. Okay, so data is having 891 observations and 12 variables. So age is having a couple of missing values as we see here. 177 missing values are there. So we are creating a variable called missing age. If is.na of training age, then it will have y, otherwise n will be there. Okay, so now we have 13 variables. So if I open the data, so here we will have the variable missing age corresponding to whatever age is missing. Now I'm adding a feature for family size. Train family size equal to 1 plus train sibling s plus parents. Okay, so that is a column having family size. So here we have family size as well. Now, now train survived. I'm changing the survived as factors, and train P class also changing to factor, sex to factor, impact also to factor. Then missing age also I'm changing to factor. Now, now I am subsetting the features into. So these are the transformations I have done for the data. Now I am changing the subset the data to features we wish to keep to use. Okay, so here I'm keeping features and features I am selecting. These are the features I need, and train data, from train data I'm taking only the features. Other variables like name and other things I'm just skipping. Now train features, I'm just subsetting the train data with the feature variables only. Now we have the data with 10 variables only. Now structure of train. So these are the variables we have. Okay. Uh, Now what we will do is we will impute the missing ages. So currently we have a couple of values missing for the age category. Um, Okay. Now Carrot package actually support a number of mechanism for imputing, like imputing and predicting missing values. Leverage the backed decision tree to impute missing values for the age feature. Okay. Now we wanted to yeah, we wanted to update the missing values. So here okay. Now here we will first transform all the variables to dummy variables. So here dummy variables are like we are creating using this function called dummy was, and we are using all the variables to dummy variables. So and we are taking the train data and just skipping the first variable, that is the target variable. Survived or not, that is our target variable. So I am just skipping the first variable and creating the dummy variable. So here is the dummy variable, dummy data. So here this is the dummy data we have, and from this dummy variable I'm just trying to create a train dummy. So that is why predicting the dummy variables to train data. Okay, so now I'm just creating the train dummy, and here I'm just creating the train dummy, and here this p class there will be three values, so we are creating dummy variable for that. So if this one if category is 1, then we will be having 1, otherwise all the other values will be 0. And here you can see here it is 0, 0, it is 0, and corresponding to class 3 we have number 1. So this is actually we are transforming the existing variable into a dummy variable. Okay, because for classification model we actually need these kind of an approach, so that's why we are just transforming this one. Okay, um, so we are transforming into the dummy variable. here we have the dummy variables, and for sex also we have the dummy variables. If it is female, we will be having 1, otherwise 0. For male, we will be having 1, otherwise 0. And age also we have keep the age variable like that, because numeric variable we don't need to uh, encode the or create the dummy variables for numeric variables. Okay, for factor variables we are creating the dummy variables. Now we will be impute the missing value. So pre-process function is there. So there we are passing the dummy data, so train dummy data with created with dummy, and method we are putting big bag impute. Bag impute method is actually for bag impute we are using this packages also, like IPRED. IPRED package is used for bag import. So for pre-processing and all, here we use the bag input method. Okay, so bag input method is uh, technique used for filling the missing values in the data. It actually use the ensemble learning method, or kind of bag decision trees algorithm it's actually using. So how it is actually working is, it actually treating each variable with missing values as an outcome variable, and using the remaining variable as predictor variable. And based on bootstrapping, parallel training, and prediction and aggression method, it is actually creating the or it is imputing the missing values in the data. So this is actually the process it actually take in place. Now we use the bag impute function, and then imputed data will be predict, using the predict function we use the pre-process and train dummy data, so we will be having the new imputed data. So now the imputed data will be look like this. Okay, so here all the ages are actually uh, imputed. Okay, now we have the age imputed. Now train age, we are updating the train age using the imputed data age column. Okay, so imputed data age column is 1 2 3 4 5 6 column. So we are imputing the 6 column to train data age. Okay, now our train data will be like this. Okay, we have updated the train data. Okay, any question till here? Any question till here? Why we do replace the missing empire value with the mode? So okay, so when it comes to the this one data, so okay, where's the data? Okay, so this data, so survived is basically did they survived or not. Then P class is the ticket class. Okay, passenger class, or passenger class data. So one, two, three, first, second, and third class data. Then we have sex, age, and sib sp means a number of siblings, and parch is number of parents uh, or children. Okay, and fare will be the there was ticket and name and also that was there, and fare will be the passenger fare. Cabin is the cabin number and all that was there, so we skip that one. And then we have this embarked one. Embarked is the port of embarkation. Okay, which port actually they have embarked the journey. Okay, so that is what embarked means. So some, if there are some values are missing, we can replace with the maximum one, because we are not sure which port they have loaded. So we are just using the port where most of the people logged in. That's all. So it will be replacing data will be based on some some practical thoughts, like how we can replace. And also here embark thing is actually a data error. If some missing values are there, that is actually a data error. So that we cannot actually go and check with the uh, data entered team. So that's why we are trying to replace it with the maximum observed value, because when we check the table here, mm, okay, when we check the table here, so here vast majority of the people are actually loading from one station. So that station we can add couple more people also if they are missing. So that won't affect the data much, okay, or our model much. So that's why we are imputing that with the um, maximum number. Okay, so that is the reason we are imputing like that. Good question. Any other question? Okay. Okay. Now, okay. Now we'll move on. Is the regression is supervised or unsupervised? Okay, that is a good question. So, what do you think? Regression is supervised or unsupervised? Anyone from the audience, you can also respond here. Like, okay, supervised. Okay, Binda, you are also replying to your own question. That's good. Any other answers? Okay, supervised. Right. So basically, the regression analysis is a supervised learning. So why? Because in supervised learning, we basically need these two things. Like um, one is we need a target variable, and then we need some predictors as well. Okay. So basically, what is a supervised learning is simply if we have something we can point it to. Okay, so we will be having a dependent variable, and based on some independent variable we try to model the dependent variable. Whenever this situation is there, that is actually called the supervised learning. Okay, so if we can label something, it need not be a regression itself. Sometimes the classification models also falls under the supervised model. Okay, sometimes classification model will fall into unsupervised model as well. So but regression is actually a supervised model only, because we'll be having some input features and target variable will be there. The model learned using the label data only. Okay, because every time whatever the target variable or whatever the response in a variables like input variable, input features and all, so that should be labeled, that should be properly labeled. We should know what exactly the value should be. And also in regression the output is actually a continuous value. Okay, so it's not a class and all. So it should be a continuous value. For example, sometimes we look into price variables, sometimes we look into salary or those kind of things. So it's actually not a classification, a categorization. It's a continuous variable, so it's a regression model. Now, why it is not supervised? Because sorry, why it is not unsupervised? Because unsupervised learning does not need any like target variable and all, and it not need to have a correct output to learn. Okay, so for example, AI camera, if you look at the AI camera, it actually classifying the image into is if people are putting the helmet or seat belt and all. So it actually making the prediction based on the classification. Okay, or in basket sorry, basket analysis, like market basket analysis and all, or customer classification and all. So there we don't need any target variable. It is actually simply looking at some information, it will simply classify based on some probability. But regression is not like that, it has a target variable, so it cannot be unsupervised. Okay. Mm, okay, so that is why it is supervised. It is not a unsupervised condition. We don't have an unsupervised condition for regression analysis. Or Benita, if you come across any such as examples, even I am eager to explore that. This is the best of my knowledge. Okay. Okay. Yeah. Now, mm, any other questions? Otherwise, we'll move on. Okay, now we will split the data. So here we will split the 70 30 percentage, 70 percentage for training and 30 percentage for testing we will take. Now we will set a seed. So this seed is actually for keeping the randomness same throughout. So here we are creating an index, that is creating data partition function we are using here, and we are passing the data train target variable survived and times equal to 1. Then the probability for testing train data is zero point 0.7, list equal to false. Now we are creating these indexes. So here it actually created indexes. Now some random indexes are actually taken here. So it actually have the 70 percentage of the indexes in the data. So we only have 625 index covering the 891 observations. So based on these index, we will be taking the train data and test data. We are splitting it into train and test. Okay. Now we will be having train data. Titanic train will have 625 and test will have 266 observation. Okay. Now we have the training and testing observation. Train data we will be used for training, and test data we will be used for testing. Okay. So now we will create a proportion table, like what is the percentage of survived and non-survived. So survived percentage is 38 percentage or 38.38 percentage in train data, and 61.61 percentage of non-survived people. Uh, Sorry, this is for actual data. Now we will be using the same for train data. Train data, it's also almost the same. and test data also it is almost the same. So make sure this proportion is almost same when you splitting with the train data and test data. So that is very important. Otherwise, it will be biased. Okay. So mostly when people are creating the samples and all, they won't actually check these things. Sometimes because of the random states you have taken, it can actually differ. Okay. Uh, I'm not saying it should be exactly same. 61 and 38% should be keep throughout. But it should be kind of, it can be 60 and it can be 40 also, or it can be 63 and this can be 37 also. But the thing is, it should not be something 50 for train data, and for test data it should be 65. That should not be the case. Okay. So for training and testing data, this is very important. For training and testing data, the proportion of the target variable, if that is a classification, the target variable, and if it is a continuous variable, the characteristics, the 5 number stat characteristics should be somewhat similar. Okay, somewhat close to for the actual data, train data, and test data. Okay, so that is also important. So you need to check those things. Okay. It should be somewhat similar. Now we will train the model. So first, as a machine learning model, we will create a train control here. So that is for the training control. We use the train control function, and we'll be using this repeat this method. Okay. So repeated CV. CV is cross validation. That is the repeated cross validation method for training. Okay. So that is the method we will be using, and the number of training will be 10 number of iteration will be there, 3 repeats will be there. Then search is actually based on the grid. So uh, this is this function is simply repeated cross validation function. It is a supervised model evaluation method, and to get a reliable performance estimate. Okay, so that is why we are using the train control function. So instead of doing some simply one cross validation, it actually repeated multiple times with some split. So here it actually repeated 3 times with 10 split. Okay. So here we are setting up to perform 10-fold cross validation repeated 3 times to use a grid search of optimal model. Okay. This is a hyperparameter tuning technique also. Okay. So okay, so that is the method we are using here. So why we need this model? So normal cross validation can be a bit unstable depending on the data and its split. Okay, but here repeated cross validation reduce the randomness in the modeling, and it also gives more robust accuracy and help the model comparison more clear. And it is actually preferred for a small or medium sized data set. As we have a small data set here. Mm, okay, let me, it actually stops in between, so let, give me a second. I think it is due to some memory issues. uh, so okay, then give me 1 second. Let me do one update here. Okay, so yeah, okay. So sorry for that. I actually some memory issues there. That's why the screen share got stuck. Okay, if that happen again, just let me know so we can clarify that. Okay. So okay. So here that repeated CV that is actually helpful this one. So mm, okay, this is the use for the repeated CV. Okay, method for in training control. So I'm just running this one, and we will be tune the grid, leverage the grid search of hyperparameter from our XGBoost. So okay, here this is a reference. You can actually go through that, and here we are creating the grid tune. We are using the expand grid function and expected okay, so here we are changing some of the hyper parameters for our performance, so that will improve the uh, grade as well. Now we will go through each of these things. So here it actually create all the possible combination of xg parameter sorry xg boost hyper parameters, and expand grid function generate a data frame of all parameter combination. Each row one model configuration will be there. So here tune okay, let me first run this one and tune grid. Mm, okay, here okay, each row will have one model configuration, and caret train one model per row. So this is a model configuration. Now, mm, when we looking at the parameter by parameter here, so first one is eta. Eta is actually control how fast the model learn. Okay, smaller value will be slower learning, and larger value will be faster learning. Okay, so lower eta usually need more decision trees or more tree based models, and now we have a number of rounds. Okay, so number of boosting iteration is actually, or a number of trees actually it mentioned. So here we are using 3. So it actually more rounds will be more complex model. Now maximum depth. Okay, so it actually control the complexity, and deeper trees actually capture complex pattern. Okay, if the tree is more deeper, that will be help us to capture more complex patterns in the data. For this one we don't need a much deeper tree. If the depth is too deep also, then uh, it can cause overfitting also. So like if the values are 3 to 5, then it is actually a simple model, and if the values are from 6 to 8, that will be a median complexity will be there. If it is 10 plus, then there will be risky models will be there, so we need to watch for those models. Now minimum child weight, that is the minimum sum of weight in a child node. Okay, so main node will be there and child node will be there for a decision tree models, and so the minimum sum of weight in a child mode is what it actually represent. And calls so here minimum child weight higher value will be more constructive split will be there, and higher values will prevent the overfitting as well. And now call sample by tree, that is a fraction of features used per tree. This add the randomness in the model, like in random forest and all, and it reduce the overfitting as well. Here 0.03 sorry 0.3 is actually 30 percentage features per tree, and we are using 50 percentage as maximum here. Now gamma parameter is the maximum loss reduction needed to split. So here we are keeping 0. 0 means there is no restriction in the model. Um, this is actually for non-penalized model, and if we need some penalized model and all, there we need higher gamma values. Okay, but if the value is higher in gamma, that means there will be some there will be only few split will be there. Okay, then subsample, this is actually the fraction of rows used per tree. Here we are using one fraction of row, that is all rows we are using. Okay, so the lower the value help us to reduce the overfitting as well. So here we have this model. So this is the tuning tree we have. Okay, this is a model we are passing. This is the grid we are passing. Now we will be use the do snow package to ensemble Carrot to train in parallel. While there are many package options in this parallel processing, do snow has some advantage of working in both Windows and Mac OS. So that's why we are using. If we are using the parallel and all, that will more compatible with the Windows only, not with the other things. So that's why. Now we can also use the parallel library as well. So I'm just commenting it for the time being. So okay. Now I'm making this cluster here. So this is I'm creating a cluster here and creating this okay, I'm creating this cluster and with a maximum cluster equal to 10, and here I'm using the type um, okay, so psoc, so that is the time I'm using, that is the socket based workers. So there will be 10 clusters, 10 parallel processing will be there, and mm, so from this grid we will be using 10 parallel processing at one time. So and psoc is actually the kind of socket that is actually mm, it's a socket we are using in, it's actually related to the OS and all. Okay, so we are creating that cluster, and now we will register the cluster with do snow. Okay, okay, now it is actually created this cluster. Now it actually register with do snow. Okay, now we will train this mode. We will convert. Okay, let me share it once. Now we will share. We will create a training one. We will be converting it into factor. Okay, give me a sec. Okay. Okay. Now I think. Okay. So I think the screen is visible now. So here now we are trying to create the survived one as a factor with level 0 and 1 for died and survived. Okay. So we are updating that one. Okay. Now we will be using the XGBoost function to train the XGBoost model using tenfold CV repeated 3 times and yeah, and a hyperparameter grid also have been created for optimizing the model. So we'll create the caret CV, that is cross validation, and we'll be using the train function to train the model. So survived against all other parameters we'll be taking, um, and data will be Titanic train. So Titanic train is the data. Missing is. Okay, missing age is not needed. So I think we'll update this one from here while training and test fleet. Okay, train. So missing age will be missing age. Train will be there. Okay, let me replay as well, and let me reload the data from here. So just to make some update, just to remove that one variable. So okay, now our train will not have this one. So yeah, that is removed. And index we have created, and training and test we have created. So the ratio is same now also. Uh, okay, this the tune great, and yes, now we have the cluster and register the cluster. Now the Titanic column updated, and we will do the training model. So here it is, the model is actually training. So here you can see it's actually working on. might take some time working with this one. Mm, there is some error. Additional one nominal train workflow train for training. There are missing values in the resample performance measure. Okay, accuracy and metric values are missing. Let's check this one. It's not created. Okay, it's showing some error here. Let's let's let me try with this one once again. One second. Okay, so instead of no, let me try register to parallel. And a integer missing values in the object. Okay, so it was actually working fine earlier. Hmm, not integer, not integer. Stop this. Let me put this one. Let it go. 8 cores are there, then register this. Okay, let me remove this type and let it select its own type. So CL is this one. So let's register. Okay, there is 8 cores are available in the model and this one. Mm, okay, it's not working here. So let's try this itself and Why it is showing NA? Mm, 14, nothing is missing here. Mm, nothing is missing here. Mm, let's let me instead of gradient boosting tree, let me try with D trees. Uh, T- okay, that is for decision tree. The GX tree will be gradient boosting tree. Okay, okay. Let me actually try with this one for, also. Um, just creating a data right. So, oh, I think here I have updated this one. So, okay, let me run the data once again. So there is one change in the data. So, mm, okay, now let's see because maybe that this Titanic server part I have ran 2 times. That's why it's showing that a null option. So it's still processing. There is still errors on this one. Not sure. I think it was actually working earlier, but not sure. So let's not waste more time on this. I will simply show you an example with the iris data. So I think so here I'm just loading the data iris, and so iris data everyone will be familiar with. And here we can create the same way, like we'll split the data into train and test. So here I'm creating a data partition like iris dot spices into point 0.7, 70% and 30 percentage, and thus taking the training and testing data. Okay, now so I'm using the control, like train control will be like model, CV model I'm just using, and number will be 10 numbers I'm using. And let's create a decision tree here. So I'll be using this one. So this is actually create a decision tree. I'm creating use the train function, and spices I am using against other variables. So iris data we will be having species here, and sorry, species here, and other variables will be there. So I'm creating again species against other variables. Data will be train data, and R part is for this one. Yeah, R part is actually for decision tree. There are different models available in Keras. One is linear regression. For that we can use the LM function itself. Logistic regression, for that we can use GLM, generalized linear model, as we look yesterday or day before. And for other Poisson regression or other regressions and all, we can use the GLM function. Decision tree we will be using RPart, this one, and random forest we will be using RF. Support vector machine we will be using SVM radial SVM radial function we will be using, yeah, and KNN we will be using KNN. Navy based we will be using NB. Okay, so these are the models we'll be using, and here this model will train, and yeah, that is trained, and this is the model we are actually having. Okay, so this is the decision tree model we actually get. So here we have this model, and the parameters are as follows. And so here we have 105 samples, 4 predictor variables, and yep, sorry, 4 predictor variables, and then 3 classes are there. 3 classes are there, as you can see here. Um, okay. So for predictor variables will be these things, like these 4 variables: sepal length, sepal width, petal length, and petal width. And then other classes for the target variables is these 3. Now we have no pre-processing here. We didn't apply any pre-processing here. And resampling method, we used a cross validation with 10-fold. So so it will create 10 validations together, not one by one. um, so here, now summary of sample size is actually here we created in each fold, we actually created these sample size, like 95, 93, 95, 95, etc. These are the sample sizes created in each of the fold, like um, that is 94 to 90, 6 samples were used for training and remaining used for validation. Okay, so here this is for each of the iteration. Now resampling result across tuning parameters are given here. So CP here is complexity parameter. that is actually controlling how much tree is burned, and higher CP is simpler tree, and lower CP is more complex trees. um, Here we have CP equal to 0 for the first iteration, and for that 94.5 percent accuracy is there, and the kappa score is also 91.68. That is best performing model throughout these, and that is the deep tree is there, and minimal pruning is there. Now second model, we have 45.71 percentage CP, that is complexity, and accuracy here, as the complexity increases, accuracy drop to 79 percentage, and kappa value also drop to 70 percentage. So here it means more pruning is there, lost of useful splits are actually happened there. When the complexity parameter increased to zero point 0.5, the accuracy is decreased, or it dipped to 39 percentage, and tree is too simple, and it actually goes an underfitting because kappa is actually 0.12. Now the criteria here is accuracy was used to select the optimal model using the largest value, and the final value used for the model is CP equal to 0. Now the final model we have is CP equal to 0. That is this model we actually used. Now we can use the predict function to predict the model. So here we can use the predictions and confusion metrics here. So the predict will simply give you the prediction like this. So let's predict this. So this is the prediction. We will come to that. We will first use the confusion metric. That will be easy to understand. Okay. Now this is the confusion metrics we have. So okay, so now the confusion matrix is actually telling us these things, like first one is the reference, the prediction, and actual values. Okay, so this is the actual values, and here is the prediction. So here you can see for this class it's actually predicting properly, everything is classified properly. When it comes to here, it actually classified 14 in correct order and one in the wrong model. Now here it actually, when it comes to the last class, it actually predicted 13 on correctly and 2 wrongly. So accuracy is 93 percentage, and the 95 percentage confidence interval for the accuracy is 81 percentage to 98 percentage. Then no information rate is 0.33, and here now information rate is simply saying accuracy if you guess the majority class every time. Since the classes are balanced, so the classes are balanced here, so it's actually 1 by 3. Okay, three classes are there, so so now information rate is actually 1 by 3 here. That is actually a better information. Now the p value for the accuracy, so that is actually less than 0.05, so that is statistically significant, and model performance is not random from there. And kappa score here is the measure agreement beyond the chance, so that is zero point 0.9. So kappa is actually range between -1 to 1, and when the kappa score is less than zero point 0.4, that is poor. Zero point 0.4 to 6 we'll consider moderate. 0.6 to zero point 0.8 it will be good, and if it is greater than zero point 0.8 it will be considered as an excellent score. So here we have a good score. Now statistics by class here. So here sensitivity is actually good here. So it has a ability to correctly identify each class. That's everything is actually good. And for this one, this class, this model is extremely performing well. And this is the class, it's having some trouble, but the score is actually good. But still, this is a class having some uh, some hard time. Okay, then specificity. When it comes to specificity, ability to correctly reject the false class. So for this one, it is actually perfect, and here it is actually decreasing, and here also it is good to decline the classes. Okay, then positive prediction value, that is precision. Negative prediction value, that is recall. And then the balance accuracy, we need to look, that is also good. Okay, so overall accuracy of the model is 93%. That is actually very good. And we got a perfect classification for this one, so everything is classified properly, so that is satisfying here also. And minor confusion between these two classes, that is a very minor one or negligible. Then kappa is very high here, that is excellent value for kappa, that is a good model. So that is actually saying that the model is actually generalized to test data. Okay, it's actually classifying the data properly. Now, okay, now we got the decision tree model here. Now we will see how we can simply try to predict the decision tree. So for that we can use the rpart plot function. So if you simply plot the model, we'll be getting the model like this only. So we won't get any useful information. So for that we can use the library rpart plot. Okay, so I think that is not installed, so let's install. Okay, so library this one, and I'll plot the final plot. So this is the decision tree for this model. Okay, so this is a decision tree. So here, this is the classification we are actually having. Okay, now, okay, so here, here this is actually Setosa, that is the species we have. So that is actually classified properly. So here it is actually checking petal length is less than 2.6. If yes, it is actually classifying to Setosa. Okay, and if that is no, here is the classes, and if it is no, then it is actually considering uh, vesicolor. So versicolor, there is a chance point point 0, point 0.5, point 0.5. So for these two things, so here it's again checking like if the petal width is less than 1.7, then it is actually going to vesicolor. Otherwise, it is going to virginica. Okay, so that is actually the way we explain this plot. Mm. So this is the how we interpret this one. Okay. This is the way we interpret this plot, and this is how we are making the decision. So here it is actually mostly the decision is based on these two things. Um, okay, so this is the plot here, and we can also do one more plot here with the text and plot. So now we can actually do the okay, we can actually do the this thing like um, hyperparameter tuning for a better model and all that we can definitely do. There is a scope for hyperparametric tuning in all the machine learning model as well. Okay, so okay, there is a question like so what is mean by kappa? Okay, kappa is a coherence kappa. It's actually how it's saying how good your model predictions are compared to random guessing. Okay, that is what actually kappa means. So kappa is actually calculated using like uh, observed accuracy minus expected accuracy divided by 1 minus expected accuracy. So that is what the formula for kappa is. Okay, so it's the ratio between observed and expected accuracy to the total false accuracy. Okay, so that is the calculation for this one. Okay. Okay, so this is how we can create this model. Uh, Now we can also do a couple of things here. Like here we have the controls and all. So we can actually expand these things by creating the this thing like hyperparameter tuning and all. So we have a lot of hyperparameter tunings and also for example CP grid we can actually expand. So CP I am putting like this. The CP values I am taking like this, and okay, then I can keep the control as this. Okay, so I'm using the controls repeated CV. Above we just use the CV only. Here we are using the repeated CV and also created the grid as well. And now we can use the cart model like. mm, okay. So cart model spices data equal to train data part control CP grid is the tune grid. So based on this we can again update the model with the hyperparameter tuned. So this is actually created and the tuned model will be like this. Now it is a bit tuned and though here we can see the CP parameters. We have created all these CP parameter and see the performance. Here it is actually performing like this. And if we simply plot the one like if we simply plot the tuned model, so the model is actually consistent with these control parameters. And we can do the predictions and confusion metrics. Here it is again again the classification is same, but actually this is because we have a very small data. Iris data is a very small data, that's why. Otherwise there must be some changes. So we can put the final model. It's again the same, but sometimes it will actually change if you have a large data and all. mm, Again we can yeah, we can try another models as well like So you can try RF grid instead of decision tree. I can go for random forest. For that, I'm creating a RF grid, and I'm creating a training model for RF model. Like uh, this is the random street and random forest model. I'm okay. RF package is not installed, so random forest is like it's actually more trees into the model. So instead of a single model, we will be using random forest. So why I am showing this carrot function today is because most of the time when I've seen like in most of the workshop titled machine learning and all, so many people are actually showing only the simple linear regression or a regression model or decision trees or these things like a random forest and all with the training and tested data, and they are simply saying this is the machine learning model, but it is not. For machine learning model, we have these kind of uh, learning processes there. It's not simply putting the model and putting some splitting the data into training and testing and putting it into the model. uh, it is actually we have these kind of parameters, hyperparameters, that is actually a plays an important role. It's not one time training of the model. If we are training the model only one time, if you are performing the model only one time using some direct formulas and all, and creating the model and predicting and comparing it with the test data, it is actually a statistical model. It's not a machine learning model. Okay, so in future, if somebody explain you in this way, like if you have a data, for example, I'm simply explaining a linear regression model. So if somebody is actually coming with splitting the data into training and testing, and then asking or then they are predicting the model, creating the model and predicting the model, and then they are coming with this thing like uh, okay, then they are coming with this model like they are simply predicting that model and comparing it with the test data and comparing creating the accuracy metrics like RMSE and all. It is not a machine learning model, it's still a statistical model. So a lot of people are actually giving that false impression to students. That's why I just introduced these things. Now uh, this is the way we need to create multiple model iterations and all using these hyperparameters, and then we need to um, do it. Okay, then we need to create this model. Otherwise we cannot perform a machine learning model, that will be a statistical model. Okay, so this is the again the confusion matrix for random forest model. So it is also the same as you can see. So here we can have the variable importance and all. So petal width is actually a main variable here, and followed by petal length. Sepal length and width is not contributing much to the model here for the random variable, random forest. So variable importance plot we can do it. Mm, okay. Okay. So So this is a variable importance plot for random forest, and mm, mm, now we can do this plot for random forest one using this PDP library. I think this is also not installed. Okay, so okay, so this is actually the random forest plot we'll be having here with partial dependencies plot and all. If we plot RF model, this is the RF model plot. Um, so this is another partial plot for petal width and petal length, its correlation and all. And this is one plot, and so if we create a level plot as well into this one, so it will be like okay, this is the level plot. We can also do a plot. This is how we can think there is something in the geom line here. Okay, let's leave it. I will explain one with one example uh, tomorrow. Tomorrow we will be discussing one complete data analysis workflow and a machine learning model in a proper real data. Okay, today I tried to get that one, but it was not went well. Okay, so now we will also look at a regression problem. It's almost the time, but I will look at a regression problem quickly. And Okay, now we will be using the MTG. So as you all know, like MTCAS data set. So this is the data set. So we will be using the mileage per gallon as the target variable for the regression analysis, and we will be creating a code like let's create a random seed, and I am creating some sample like 70 percentage of the rows will be taken for training, and then rest for testing. Okay, so now I'll be using the model like LM model like this, and using the summary like this, and then we'll use the predictions. Okay. Okay, this is the prediction for the test data. And we usually create some testing using RMSE as well. So it will tell you the model performance. It's a lower one, so it's actually a good. Now R square for the test data will be this one 78 percentage. So that is also a good one. So now we'll plot the actual and predicted values as well. Yeah. So this is the actual and predicted value changes. It's actually only few points are actually changing. So it's actually uh, um, how we actually do these things. So this is actually what people usually believe as a machine learning model, but it is not the machine learning model. For that, actually, we need to do all these process. First one is library caret. We are taking the library and we are using the controls here, training control. We are using the CV method. Okay. Um, okay. So that is a cross validation method, and 10 cross validation we will be doing. Instead of fitting one single model, we will be using the 10 on this one. And here we will be using the LM caret and train function. Then we will be using the equation, regression equation here. Data, we are passing the training data. Method, we are preferring LM. Training control will be based on this control. Okay. Now we can perform this one and okay, it will create the model and it will give you this insight. So here, this is the RMSE. It will tell you the RMSE, the R square value, mean absolute error value and all. It will simply tell you. Okay. So so this is how you need to do the updates and all. So here we can do the prediction of these model, and predictions will be like this, and we can also find the other things as well. Okay, now we can also do if needed, we can also do the hyperparameter tuning and all. So there is not much hyperparameters to tune in linear model, but we can also create some uh, like some hyperparameter tunings and all, but there is not much these things are there, like hyperparameters are there. So we can try these kind of model also. So the same model, we will be having some pre-process things will be added here. So our LM model will be like this. So here you can see earlier model was a very overfitted model, 99.2 percentage is there, but after this, adding some pre-processing, we actually getting a neater model of the uh, model. Okay, so this is how we can do some um, tunings and all. But actually, instead of linear model, what we can do is, if there are some ridge regression and all, we can actually do the hyperparameter tunings and all. So there we can actually create the grid and all. Okay. So like we discussed earlier, we can create the grid and all in the ridge regression model. So this is the ridge grid we are creating, and based on that, we can create the ridge regression model. Oh, I think the package is not installed, so it's okay. Ridge grid is there. Then we can create the ridge regression model like this, and the model will be like this. Okay. So this is a ridge regression model. So you can see here, as the lambda increases, the um, r square is also improving. And but if you see here, like in between, here actually we are having a optimized model, yeah, somewhere here. So we are having some optimized models here. So we can choose the model accordingly, based on the best values we have. Okay, so this is how we do the different regression models, or like different models in the machine learning way, not like training and testing simply using. Okay, if you're just using a training and testing data set and performing one model once, that is actually a statistical model, not a machine learning model. Okay, be sure about that one. So there is a lot to learn in terms of machine learning and all, but you can simply explore those things and concept of machine learning and all. This is kind of a starting point for that. Okay, if you have any doubt in between, you can ask now. Okay, any doubt, you can we can discuss that.